Okay, let's look at some solutions so far. So last time we talked about this very flexible design where we have an interface that defines all of the things that an entity in the game should do. We should be able to ask its name, description, ask what room it's in, and then have it move, and it gets to decide how it moves. And so some of these methods, we expect the implementation to be the same for all entities. Get name, get description, get room. Probably those are just going to return fields. Move is going to be different for each entity, we expect. So what we can do is we can provide a generic implementation for the methods that are going to be the same for everybody. And we do that with an abstract class. So here we have some fields, we have some getters and setters. We have a constructor, even though you can't actually make an instance of an abstract class. We still have the constructor because setting all of these fields is going to be the same for all instances. For all children, for all entities. But the one method that's going to be different, we don't provide an implementation for. Instead, we mark it abstract, and that means that any child that extends generic entity is going to have to implement that one for itself. And so then, for example, we have chickens. If a chicken extends generic entity, the chicken inherits all these variables. Chickens have names, descriptions, current rooms. Chicken inherits all the getters and setters. So if you have a chicken instance, you could say, mychicken.getRoom, and it would tell you. And then the only thing the chicken has to do is override the abstract move method from the parent. And a question from last time was, well, wait, couldn't you do all of this and leave off the interface? Like, why even have the interface? And the answer is the interface is sort of like an emergency safety possibility, because if we change our mind and decide that we need a completely different way of implementing get name, get description, and get room, the interface makes it safe for us to create a different class that implements the interface, and we can be sure that the instances of our new class are still going to work for our game, where they're still going to be able to fit into the data structures. So that in brief was the solution so far. Couple dilemmas people brought up. How can we make all the creatures in the whole game move? And then how does a pop star or a wumpus check if a player is in an adjacent room? So we'll come to those dilemmas in a minute. I just want to remind you of the two design principles so far, which is objects are responsible for their own actions and variables, their own business, as we said, and then hide the how, which is classes should hide their own implementation. They should hide how the methods actually work. There's going to be two new ideas which are related, which are it's very important that your variables remain consistent with each other. And a really great way of doing that is ensuring that there is one source of truth. So let's do like a really simple example to see what both of those mean. So if you look at this circle class, circles have a radius and an area, and we've got a constructor, getters and setters. This is an example I sometimes give in the intro class. This is sort of like a very straightforward way of implementing a class. It's got variables and getters and setters. So what's the problem here? See if you can figure it out. So the problem is it's possible to construct a circle where the radius is 10 and the area is 0, because you're allowed to set these two things separately. But radius and area are really just two different ways of talking about the size of a circle. So the problem with this implementation is it's possible for the variables to be inconsistent with each other. So one possible solution to this is strictly control who's allowed to set the variables. So here we still have two variables, radius and area. But notice I've removed the set area method, and I've removed the area input to the constructor. When you set the radius, it sets both variables. So if you strictly control who's allowed to change the variables, you can ensure that the one method that's allowed to change one of the variables actually changes both. So that means you're always changing both at the same time, and that's how you're ensuring consistency. You do see this kind of approach in practice. The only problem I'd say with this approach is that there's always the lurking danger that something could change and that these two variables could become inconsistent. So the really true way of making sure that your variables are always consistent is by only having one variable for each fact about your object, because one variable literally can never be inconsistent with itself. And so that's called one source of truth. So here's what that solution would look like for the circle class. We remove the area variable. So now there's only one variable that's about the size of the circle, its radius. But the API hasn't changed. We still have a set area and we still have a get area. And from the outside, that makes it look like maybe we've got an area variable, but we don't, because we're calculating it every single time based on the radius. So when we get the area, we calculate what the area is based on the radius. When we try and set the area, we figure out what radius would produce that area, and we change the radius to fit the area that we're trying to set our circle to have. So let's look at how those design ideas apply to the game that we're trying to make. There's a couple design issues here with this implementation for chicken. So chicken, remember, we're extending this generic entity. When I construct a chicken, I'm going to tell it what room it's in. And then I'm running the parent constructor. Remember that super runs the parent constructor. So I'm constructing a generic entity. Well, I'm not actually constructing it. I'm using the generic entity constructor to set the name of the chicken to be chicken. And then I set my description and I set my room. And then the move method, remember, is the only one that we need to actually implement. And so here I'm saying, let's ask my current room who its neighboring rooms are. And if the current room doesn't have any neighboring rooms, then I'll exit because I can't move. Otherwise, I'll choose one of those indexes at random from the list, and then I'll get that room out of the list and save it into a variable called next. And then I'll set my chicken room to be that next room. So all of this stuff at the top is about getting a random neighboring room. And then here I tell my chicken, hey, you are now in that room. Okay, so there's at least one, probably two problems with this. Take a minute, see if you can figure out what they are. So one possible issue is we're not hiding the how. We are asking our current room for its internal representation of the neighboring rooms, and we're using that directly. This isn't maybe such a big deal. Like, you might be saying, well, wait a minute, that's not reasonable. Like, sometimes you might need a list of all of the neighboring rooms from a current room. And I agree, that's true. So I'd say there's really, to add some nuance here, there's sort of two things that make me uncomfortable about this. It's not bad to have your room return a list of the neighbors. What's dangerous would be if that list was the same reference as the internal list for your current room. Because that would mean that out here, I could then mess with my room's list in an uncontrolled way. So if you are going to return an array list that you either construct yourself for returning or that is unmodifiable, which is a special thing you can do in Java, that means that you can't modify the list, then in that case, those would be safe. But there's a sort of a second thing that makes me a little bit uncomfortable about this, which is it does seem like a convenient action, or it does seem like a convenient question that we should be able to ask a room. Could you give me a random neighbor to yourself? So I think it makes sense for both those reasons to just encapsulate that behavior inside current room. So you can say this.current room, get random neighbor. It gives you a neighbor. If a neighbor doesn't exist, it will return null. So we can say if the neighbor was null, we'll just exit because we can't move. Otherwise, we'll set the chicken to that room. Okay, so that was the one problem. But there's a much, much more serious problem related to the lesson for today. See if you can remember what were the two big design ideas of today, and how is this violating one of those design ideas? So the data is inconsistent because there's one fact where a creature is located, but there are two different variables that keep track of that fact. Creatures keep track of what room are they in, using the current room variable, and rooms keep track of what creatures are there through an array list of entity. So here I'm telling my chicken that it's going to be in a different room, but the chicken instance is still in the entities list for the room it used to be in, and it hasn't been added to the entities list for the room that we were trying to move it to. So now the variables in our game are inconsistent. The rooms have a different idea about where the creatures are than the creatures themselves do. So that's a huge, huge bug. So how can we fix this problem? So the two solutions that we brought up before is we could have a single method that's about updating this fact about the world. And the single method would make sure that whenever we change one variable, the other variables also change. So we update everything at once. And we make it impossible to only update one thing at a time. So that would ensure consistency. The other solution would be to make sure there's only one source of truth. So either rooms don't have entity lists or entities don't have current room variables. All right, so let's pursue that first option for a minute. So we could ensure consistency by doing this. We'd say we'd remove ourselves. So when I say this, it's the keyword this referring to the chicken instance. So I'd say current room, let's remove ourselves. And you'd have to write this method. I wrote this method. And what this method does is it removes an entity from the entities list. So we remove ourselves from the current room. Then the next room we're about to go to, we add ourselves to that room. And then we change our own variable so that we think that we're in the next room. So now we've changed all three variables. So that's made it work for chickens, but the design is still a little bit dangerous because, if you come back to if you get interrupted, you get put on another project. We're imagining you're like working, at a company. If you need to extend the game 6 weeks from now and you haven't been working on it, you might not remember to do this. You might think, oh yeah, I got a current room, cool, I'll just change my current room. So that's why it's dangerous. It's because we've done the right thing here, but we haven't actually prevented the wrong thing from happening. And we're relying on our own understanding of this complicated framework to prevent the wrong thing from happening. So that's super dangerous. Don't rely on your own memory or understanding. Like, what if you leave the company and you don't tell the next person who's working on the code base, hey, this is important? Now they might do the wrong thing. So this would be a little bit better. This is the same kind of idea. Here's chicken. Inside chicken, we're going to run a move method and give it the next room we're trying to move to. And this move method gets inherited from generic entity. And it does all the updating. So here we're saying if the room that we're trying to move to is null, then don't do anything. Otherwise, let's remove ourselves from the current room. Let's add ourselves to the next room, and let's change our own room to be the next room. So what's nice about this is now if I'm going to add more creatures, all the creatures have access to this move method, which is the safe way to change their own rooms. But the reason it's not great yet is this. The current room variable is protected. And so that means that even though we've made this nice, safe movement method available to any children that extend generic entity, we're still not preventing them from doing the wrong thing. We've made it easy for them to do the right thing by running the inherited move, but we're not preventing them from doing the wrong thing because they can still access this current room variable. So if for some reason they didn't know about the move method here or they didn't want to use it, they could still, look, I'm doing it right here. I could still say this.currentRoom equals room. What if I'd forgotten this line in the constructor? What if I'd forgotten to say current room add this? Now the world is inconsistent again. So it's not just about having a method that enables all the variables to be consistent. You want to force people to use the method that enforces the consistency itself. So the way to do that is if you make your current room private, now in your children, anything that extends generic entity is forced to use your methods if they want to change their own current rooms. So it's like literally not possible for any of the child classes to change current room in a way that would cause the world data to become inconsistent. So you can see it says 2 related problems. The 2 related problems are here in the constructor. Because after I made it private, now I can't say this.current room anymore. So the solution here, do I have a solution? I lost it. Okay, so chicken, so we swapped sides here. So chicken is on the right now, generic entities on the left. So you'll notice that I ran a setCurrentRoom method in chicken. SetCurrentRoom is a method that I created inside generic entity that ensures the consistency. So it'll add the creature to the room, and it will tell the creature what room it just got added to. So now we have really enforced consistency. The only way to change the current room variable, make sure that everybody's updated. Well, we've almost done it. If we really were going to make everything consistent, we'd need to visit the room class as well and see, because remember we have these variables, or sorry, we have these methods that will remove entity like that. So we'd have to make sure, we'd have to maybe control access and be really careful about who's allowed to run remove entity. Or like if an entity gets removed, then that entity's current room also gets set to null because they got removed from a room. So as you can tell, once you have multiple variables that store the same information about the game, it can be really tricky to make sure that it's impossible for them to become inconsistent. So this is like not really my favorite solution to this problem because it's hard to get right. And there's a lot you have to think about. It makes everything feel very complicated. So maybe it would be better if we could make there just be one source of truth for creature locations. And so our options would be the current room inside an entity is the only variable that knows where entities are. But in that case, we need a solution for being able to ask rooms what entities they contain. Because now only the entities are allowed to be associated with rooms, like in their own variable. Or the other idea would be, let's remove the current room variable from an entity, and only a room's entity list knows where entities are. And each entity doesn't actually know what its own location is. But the problem with that, then, is we need a solution for how an entity can actually know what room it's in if it's not allowed to represent that using its own variable. So all I'm really saying in this slide is we need to keep the API the same. Like we still need to be able to get room from an entity because it's part of our interface. Remember the interface? Oh, I lost it. Oh, it was way at the beginning. I remember. Okay, so an entity still needs to be able to get room. That doesn't necessarily mean that we have to do that by having a current room variable that gets returned. So we're considering the idea now maybe that we don't represent that directly. Instead, if an entity wants to know where it is, maybe it needs to ask the game itself where it is, and the game will say, "Chicken, you are in this room." And then once it's done that, it can return what the current room is. Okay, so we'll think through that in a second. Let's turn our attention now, but at least this approach here would work. Just because it's complicated doesn't mean it's bad necessarily. So this is a workable solution to maintaining consistency. Okay, let's take a look at one of the other dilemmas. Let's think about moving all the creatures in the game. So inside main, I could have a method called move all creatures where I get all the rooms in the game, and then for each room, I get all the entities in the room, and then for each entity, I run its move method. So problems with this approach. So one is the same thing, not hiding the how. And I talked about this before, where it's not necessarily bad to get a list of all the rooms. We just want to make sure that once we've done so, it's not a reference to the internal storage of the game. So it could be an unmodifiable list, or it could be a completely new array list that got constructed when the getter method was run. But I think, just like the last example, it's a task that might make sense to let the objects themselves be responsible for. So instead of saying, "Hey, give me your room list," we could do this. We could have a method called move all creatures inside the game itself. So we'd say graph move all your creatures, and then inside graph it would hand the responsibility to each room. So because the graph has a list of all the rooms, it's cool for it to loop over those. And then for every room, the graph will say, "Hey room, you are now responsible for moving all your creatures." So it's a way of having each class be responsible for what's appropriate at its own level. And then a room, because it's got a list of all the creatures, loops over the creatures and tells each one to move. So this is sort of a nice way of separating out the responsibilities. But there's still a big problem here, which is a lot of entities might move twice because we're looping over rooms one room at a time, and we're updating the rooms live as the creatures are moving. So imagine there's a chicken in the hall. The hall asks the chicken if it's going to move. And so the chicken moves to the library. And now we loop to the next room, the library, and then we ask the library to move all of its creatures. And the chicken that used to be in the hall is now in the library, and so now that chicken gets another chance to move because the library is going to ask it to move again. So that's a problem. We only want everybody to move once. This is pretty much the same problem that we experienced way back when we were doing the wildfire simulation. Remember how we didn't want to update the neighboring locations to be on fire or not on fire as we were still looping over the data structure? Because it's like we're moving, like we want the world to move into the next time step all at the same time, but we have to update the parts of the world individually. And so how can you sort of get around that problem? So one good solution would be if the graph itself, if the game itself had a master list of all the entities in the whole game. In that case, in main, you could still ask the graph to move all the creatures, but then the graph doesn't ask each room. The graph just loops over its master list of all the entities and tells them all to move. And now we're guaranteed that the creatures aren't going to move more than once because we're only going to loop over each creature once in this list. You might be worried that this is making the problem we talked about before even worse. You know, before we only had entities inside rooms, and now we've also got entities inside the graph class itself. Isn't this just more and more sources of truth? But think very carefully about what we're trying to represent. The thing for which there were multiple sources of truth was the specific room an entity is in. And we haven't represented that again if we have a list of entities in graph. Because a list of entities in graph isn't recording where entities are. Yes, each entity still knows where it is, but just adding an array list of entities in the graph class isn't creating another source of truth for the question about the location of entities. In fact, it actually seems like this is leading us towards a nice solution for one source of truth. What if only the creatures know what room they're in, and the graph has a list of all the creatures? So in other words, what if we remove the list of entity from each individual room? So individual rooms no longer know who's in them. And the only variable that stores the location of an entity is the entity's current room variable. But the game itself has a list of all entities. This seems to work out very nicely because there's only one source of truth about location, inside entity. all the creatures can move easily because we just loop over the list of all the creatures inside graph. And the only real issue that we need to solve now is we need a good solution for how a particular room knows which creatures it contains. But remember that room is an inner class of graph. Node is an inner class of graph. And an inner class can access all of the fields of the outer class. So rooms still have access to the master list of all creatures. Cool. So what that means is that a room is free to loop over all the creatures and figure out which ones are inside itself. Probably it would be better to have a method that encapsulates that behavior. But my point is the rooms themselves no longer need to maintain lists of who's in them. The only downside to that approach is it might strike you as a little bit slow to loop over all the creatures in the whole game every time we want to know, is one inside a particular room? For the moment, I think that's the least of our problems. So I think let's go with that solution for the moment. But you can see why design is tricky. Solving one problem very often introduces a different kind of problem. So I think this is kind of a very authentic exercise in thinking about trade-offs involved with good design. Good design isn't, something that's very easy to arrive at. Very often there are trade-offs.